Hi, my name is Lisa Lorenzo, and this is my Physics 2211 Lab 5 Falling Slinky. So the purpose of today's lab is to explore a system of our choosing and then to apply physics principles that we've learned throughout the semester, and the model that I chose was the Falling Slinky. The purpose of the Falling Slinky is to observe the motion of a stretched slinky dropped from static equilibrium and to analyze by creating a model. And by using these results, we can determine if the bottom of the slinky stays stationary as seen in the video model. So some of the software they're going to be using includes Tracker, which is used to analyze the motion of the slinky, and then GlowScript, which is used to construct the computational model of the slinky. So some of the fundamental principles that we'll be looking at today's lab includes Newton's second law, also known as the momentum principle, and this can be seen by the given equation. The change F net is given by the change in momentum over the change in time, and then we can also derive the position update and velocity update formulas from this one equation. We'll also be looking at the gravitational force equation, which is the force of gravity, where gravity is 9.8 meters per second squared. And then we'll also be looking at the drag force. And in this case, B is going to be equal to the proportionality constant, which we will later learn how we're going to find this. So an overall preview we'll be looking at. First, we're going to record and observe the motion of a stretched out slinky, then use Tracker to analyze the observed motion, use GlowScript to create a computational model, and then finally, we're going to analyze results and determine if the bottom of the slinky stays stationary. So this was the given video. Some of the given initial conditions include a mass of 0.25 kilograms, a height of 1.75 meters that can be used as calibration, and then these are the following initial conditions. So the system in this case would be the slinky, and the surroundings would be everything else, including the earth, the air, everything that is in the slinky. So for the computational model, we use GlowScript, and for the first part of our code, I updated the initial conditions, the constants, and the proportionality constant, and this is found through using guess and check to try to match both of the models. So for the computational model, second part, I also created, there's two different while loops here. In the first while loop, we updated momentum principle to update the velocity and position, and then both of these while loops have updated net force equations to reflect the net force in each of these parts. So this is the following results from the lab. As you can see, the top picture is the computational model data from the GlowScript, and the bottom is both of them compared. So some possible sources of error for this include tracker error. This could be related to things like errors while manually inputting the center of mass for each time interval, because there's a lot of room for error, and this is done just by eyeballing, and there might be some discrepancies in this. The object was also observed in slow motion in the video, but the tracker does not account for this, so this could also cause some of those discrepancies that you see in the below graph. But overall, the results do show that the bottom does stay stationary for when the spring is released from rest, but once it is fully compressed, it falls as normal and accelerates due to gravity, so it doesn't completely match up. So what does this mean? This means from the results we can see that the slinky bottom stays stationary until the top of the slinky meets the bottom, and then the slinky bottom begins to fall due to gravity as reflected in part 2 of the GlowScript code, which can be seen by the second while loop, where it's the force of drag and the force of gravity. So this means that for the first part, the tension in the slinky is acting against the pull of gravity, causing the bottom part of the slinky to stay stationary. However, once it is fully compressed, this tension force is no longer there, and the spring force falls due to gravitational force bringing it downwards, so this is what causes this phenomenon. I'd like to thank you for watching, and I hope you enjoyed.